Hello! In this video we're going to try and make a connection between the spherical harmonics, which were solutions to the three-dimensional Schrodinger's equation, the angular part of that, and the eigenfunctions of quantum angular momentum. And in doing so, we'll give some physical interpretation to the quantum numbers L and M that came up from spherical harmonics. So first, let's just remind ourselves of quantum angular momentum. So normal angular momentum, you would take r cross p. And so in quantum mechanics, we usually just put hats on everything. And indeed, that's what we're going to do for angular momentum. We're going to put hats on everything. And so, for instance, the angular momentum in the x direction is y hat times pz hat minus z hat minus p times py hat, and so on for the other directions. But we actually want to put things in spherical coordinates because we want to reflect the spherical symmetry that we expect from our solutions. And so let's write the angular momentum operator in spherical coordinates, but with Cartesian unit vectors. And the reason we're going to do that is it's just going to be a lot easier to take a dot product later. And so if I write this out, okay, it's not a pretty thing. There's a lot of work that went from that first line to this line, and we're not showing all of that work here. It's not particularly a productive thing to do to spend a whole lot of time doing this. You should do it once in your life, but after a certain point, there's not much we're gaining. And instead, I want to use this result to figure out what's going on. And so first I want to focus on the angular momentum in the z direction. So let's look at the z component of the angular momentum over here. So the angular momentum in the z direction, if I were to write this in spherical coordinates, would be h bar over I partial phi. So that partial phi came from the momentum operators. Remember, momentum operators, when we promote them to operators in quantum mechanics, turn into partial derivatives. And so this is a partial derivative of the angular momentum in the z direction. And we want to know what are eigenfunctions of the angular momentum in the z direction. So let's just see what would happen. So an eigenfunction of Lz, the angular momentum in the z direction, would be something that when you operate with Lz on psi is equal to a number times psi. Well, Lz operating on psi is h bar over I partial phi of psi. Well, I know what eigenfunctions do that, or what functions are eigenfunctions, rather, that do that. Those are just exponentials, e to the I m phi, for any m. That will give me an eigenfunction of Lz. That's a pretty straightforward one to do, so it turns out then that my eigenfunction of Lz will have an eigenvalue of h bar times m. And interestingly enough, we can see that that eigenfunction also shows up in spherical harmonics. That's that e to the I m phi. So indeed, that's why there's an e to the I m phi in the spherical harmonics general formula, is because that is the eigenfunction of the Lz operator. And so then m, the quantum number m that we saw before, is actually representing the z component of the angular momentum of our particle. Okay, so that gave us some physical intuition for what the m value is. But what about the L value? For that, let's take our angular momentum vector in operator form here and take the dot product with itself. So I have L squared, the operator L squared, which is formed by L dot L. And surprisingly, it comes out nice and straightforward, not too bad, in terms of derivatives with respect to phi and derivatives with respect to theta. And actually, this should look really familiar. It was precisely something that looked like this that showed up when we calculated spherical harmonics. The partial differential equation that came out in spherical harmonics that gave us the associated Legendre functions was a set of derivatives that look a lot like this. And so what we can ask then is a similar question which we asked with the angular momentum in the z direction. What does an eigenfunction of L squared look like? Well, in general, we know that an eigenfunction of L squared will be a number times psi. And while L squared, acting on psi, is this horrible-looking expression of h bar squared and the derivatives. And so we want this to be a number times psi. And it turns out we know what this number is because we've seen this from the separation of variables that gave us spherical harmonics. We know that the number that we get, the eigenvalue that we get, is h bar squared L plus 1 times psi. And what that tells us is that L is representing the total angular momentum of the particle that we have. And in that sense, the fact that m is restricted to be between minus L and L makes a lot of sense. So the z component of the angular momentum can't be bigger than the total amount of angular momentum. It's kind of cool how that just all popped out. Like, the equations knew all about that without telling it that what we're doing is angular momentum. It all came out when we were doing separation of variables, that we had to have m between minus L and L. And now we see it has this really nice physical interpretation. So there's really cool structure that's underlying the spherical harmonic solutions to the three-dimensional Schrodinger's equation. Okay, so now we have an interpretation of our spherical harmonics as eigenfunctions of angular momentum, both total angular momentum squared operator and the angular momentum in the z direction. And we have an interpretation of L and m as the total angular momentum and the angular momentum in the z direction.